So anyways, we're coming up on 4:15, and that means it's time for the main event. So Murphy Brothers Contracting welcomes the rest of our audience in for today's credited presentation, which is Durable and Resistant Retrofits, Solving with Stonewool Insulation. And hold on to your seats, everyone. This is an HSW AIA approved credited session. So I am your host, Michael Murphy. On behalf of Murphy Brothers Contracting, we thank you all for joining us for today's presentation, coming to you live on the ubiquitous Earthkind Energy Zoom platform. As many of you know, Murphy Brothers Contracting is known throughout the greater Westchester, Lower Hudson Valley, and Southern Fairfield region for award-winning commercial and residential construction projects. The Murphy Brothers team would love to work with you. So visit our website at murphybrothers.com or call us at 914-777-5777.
First, thank you, folks. Earthkind Energy represents commercial clients in clean energy transformation that reduce their energy costs and their carbon footprints. Got a host of experience over the years with some of the clients on this page that you might recognize, excuse me. And just to give you a sense, I mean, just a few projects that we brought into lately, a single family home that was doing a 13,000 square foot home, spending a lot of money on making that a beautiful home. And they would have missed $150,000 worth of utility incentives, except for the fact that they brought us in. Could have had a lot more in another project, which was a mixed use retail and market rate project, which would have had $250,000 worth of incentives, but then wound up with $90,000 worth of incentives, which was great. Now the single family residential got $191,000 worth of incentives plus 26% federal tax credits. So if you think geothermal's not for you, clean heating's not for you, think about it as Tom Glass said, you know, for our air source heat pumps, there's tremendous incentives for ground source heat pumps similarly. And then when you do the whole enchilada and you combine solar with clean heating and cooling technologies and also electric vehicles and charging stations, you find a very cost-effective option and tons of incentives that make things work. Once again, for those who haven't seen this before, lots of incentives out there right now, over $2.5 billion plus tax credits, low interest financing, energy as a service. And if you don't do this now, just as this happened in New York City, Local Law 97 is coming with the Climate Leadership and Community Protection Act statewide. And basically what that means is that you will still be having penalties as well as changing energy codes, which are going to make this very, very dramatic very soon. So I'm Ron Kamen, Earthkind Energy Consulting. Go clean, save green, don't leave money on the table, and don't overpay for what you don't need. Thank you very much.
We'd also like to thank our media sponsor, Westchester Home Magazine. I did, Ron, really, I did. Anyways, if you need your AIA credit for this presentation, you haven't already, please send me your 8-digit AIA number. All you in attendance will receive by email, and this will come from our good friends at Rockwell, an official attendance certificate, and they'll record your credit. So during the presentation, Mr. Earthkind, Ron Kamen, will be collecting your questions for our presenter in our official Zoom chat box, and we'll tackle these questions once Todd is finished with his presentation, which means you're all on mute, so sit back and enjoy this HSWAA credited presentation, Durable and Resilient Retrofits, Solving with Stonewool Insulation. Our speaker is no stranger to our audience, having presented several times already in the past couple of years, including he did the last known actual live presentation that we did in February of 2020. And we got to get the band back together, guys. So, but until that time, we're delighted to have Todd Kimmel, the New York City Architectural Manager for Rockwell Insulation and the chairperson of the Rain Screen Association of North America, with over 20 years experience working on facade systems and building enclosures. Todd holds technical leadership positions for multiple leading product manufacturers. He is a certified passive house designer and currently sits on the board of directors for New York Passive House. Todd is coming to you live today from somewhere in sunny Brooklyn, New York, and he predicts with all certainty that the Buffalo Bills will not win the Super Bowl this year, much to my dismay. Here's Todd Kimmel.
Thank you, Michael. That's kind of an easy prediction, I think, at this point. So I'll take it. But thank you to the Murphy Brothers Contracting Group for having me in. Thank you to Ron from Earthkind. This is terrific to have you kind of leading off and managing a lot of the maintenance duties here with the Q&A. Thank you to Tom too for opening up. It was great to hear a lot about ice air, and I think there's a lot of crossover to what we're going to be talking about here today with durable and resilient retrofits. We're not going to get too deep into mechanical systems with this discussion. We're going to be talking about kind of the passive elements of the envelope, but the mechanical systems go hand in hand with this, and it's really good to know that there's folks out there addressing those needs, particularly with local law 97 looming. So I will jump in, and so I've already gotten a healthy introduction from Mr. Murphy, so I won't go too deep in here. But just so folks know, I am the architectural manager, as Mike said, of Rockwool Insulation here in New York City, and a great resource for you when it comes to product decisions, product design, implementation, application for thermal and acoustic insulation, both commercially and residentially. And I'm going to leave some time at the end of this program once we get through Q&A to really connect the dots with kind of the conversations that we're going to be having here as part of the AIA CEU program. So I'm going to really just jump right in. The learning objectives, if you guys didn't get a chance to look through this before signing up, we're going to kind of start with the overarching kind of concept of why are we retrofitting, understanding how renovation and retrofit fit within the energy conservation strategy of our built environment, particularly with our efforts to reduce greenhouse gas emissions. Retrofits are a critical element of that, no surprise. But with that, as we kind of address retrofits of our large commercial and our residential buildings, we have to recognize durability is really paramount, right? We don't want to retrofit today just to realize that we've compromised the integrity of the building, leading us to have to retrofit again or tear down in the future, right? So we're doing this to kind of save operational carbon emissions for the foreseeable future. And so we need to make sure we're doing it in a safe and durable, robust manner. So when we talk about building science, when we talk about the other elements of kind of just integrity of the building, all of those things need to come into play. And so with that, we're going to kind of review 3 specific case studies around Stonewool, the use of Stonewool insulation in these retrofit endeavors. We're going to be looking at 2 exterior retrofit options, both an Efus overclad and a rain screen overclad. And then we're going to also look at those scenarios where we don't have the luxury of putting cladding or additional components on the outside of the building, whether or not we have lot line issues, or if we're dealing with historic masonry buildings, sometimes we have to do it on the inside. So we're going to get into that as well. And we'll also touch on other considerations, right? So when we talk about reducing operational carbon in our built environment, we also want to think about embodied carbon in the materials that we use. We want to think about the other benefits of retrofit when it comes to thermal resiliency and passive survivability. And then the other things around health and safety and well-being of occupants from a fire perspective, and other types of environmental challenges. So just a brief overview. And so to no surprise, we're here to talk about the use of Stonewool, and just to kind of reduce any sort of confusion, because there's lots of terminology, lots of terms out there to kind of understand when it comes to mineral wool, mineral fiber, fiberglass, stone wool, slag wool. So I just thought I would start here, and just so everyone understands, right? So mineral fiber is a generic term for any of the fibrous inorganic substances that we can use in the built environment. And those can be classified into 3 subgroups. One is fiberglass, which I'm sure many of us are familiar with. Pink low density bat insulation, which we oftentimes see used in our partition walls. So that is made of clearly of glass fibers, products including yarns, fabrics, insulation, and other structural objects or parts. Mineral wool is another subcategory of mineral fibers. And so mineral wool is made from a combination of 2 primary ingredients, one being virgin stone, volcanic rock, which is typically basalt. And then the other component is the recycled content, which comes from the steel industry, which is the slag, or the byproduct of iron ore when you're producing steel. And so those 2 ingredients make up the predominant components within mineral wool. If you have a higher percentage of stone, you're what's considered a stone wool. If you have a higher percentage of the slag, you'd be considered a slag wool. So we're going to be referring a lot to stone wool throughout the course of today's presentation, which means we have a higher stone content in these materials that we're referencing. The last kind of category under mineral fiber is what we call refractory ceramic fibers. And these are not used so much in the built environment. They're really meant for industrial or high temperature applications. So, we oftentimes don't get confused within this kind of subcategory. And so just to emphasize again, the manufacturing of Stonewool uses predominantly basalt rock and steel slag. We heat these products up to very high temperatures. They're then cooled off and spun into fibers, not too dissimilar from how we make cotton candy. But instead here we're talking about stone. And so then that stone fibers are then collected into either lower density bats for interior applications, or they can be formed into higher density or rigid boards, which you would typically see for exterior applications or below grade or low slope roofs, right? Higher compressive strength products. And so Stonewool really can benefit the industry in terms of being able to supply materials that meet any need, right? So the density can kind of cross the spectrums of what we see with other materials. So for instance, fiberglass is typically a lower density product used in kind of those kind of flexible applications or interior applications. And then when we look at foam plastics, which are made typically more rigid, are used for the building envelope, whether or not we're talking roofs, walls, foundations, et cetera. And so Stonewool, again, based on the versatility with their density, can really apply to any of these applications. So I'm just prefacing that because a lot of the content and the solutions we're going to be talking about, again, refer back to what we call Stonewool. All right, so why are we retrofitting? I think many people on the call are probably already familiar with the challenges of climate change and what's happening right now in our world. And we have to understand that buildings, generate nearly 40% of our annual greenhouse gas emissions globally. When we talk about cities and urban environments, specifically, let's say New York, it's a much higher percentage, right? So it's at about 80 to 90% of the greenhouse gas emissions are coming from our buildings. If we don't take any action on the energy consumption that's coming from these buildings, it's expected that it will rise 50% by 2050, whether or not it's through the existing buildings we have or the buildings that we're going to be constructing moving forward. And so the big challenge here is that our typical renovation rates globally is about 1% to 2% of that building stock. So if we're going to be making a huge dent in climate change, particularly in our urban areas, we have to do a much better job than just addressing 2% of our buildings, which is why we're seeing things like Local Law 97 and policies and requirements come into play to help really make that dramatic decrease in the operational carbon of our buildings. And so when we look at the enclosure, right, it doesn't make a difference what climate we're in. The impact that the enclosure has on the energy use is going to be relevant wherever, right? And so when we look at building envelope, we look at the energy use of our buildings and kind of what's impacting the environment, we're looking at heating, we're looking at cooling, and we're looking at ventilation. And so when we look at office buildings, for instance, with these two pie charts, whether or not we're looking here on the left at office buildings in Canada, obviously cold climates, or if we're looking at office buildings in California, much more moderate climates, the pieces of these pie that make up space heating, space cooling, and ventilation all equate to over 50% of the operational energy usage in these buildings, right? So they make up the biggest chunk, whether or not we're talking hot, cold, or moderate climates. And so our envelope has an impact on how we perform. When we speak to retrofits, I'm not going to get into all of this here, right? It's just really speaking to the spectrum of either doing minor retrofits, where we're sealing and caulking items with spray foam, really kind of low cost items, upgrading lighting systems. And as we move to the right here, we're talking more major retrofits, sometimes adding insulation, replacing some windows, maybe updating some of our systems, installing sub-metering, which we're doing a lot of in New York City. But the emphasis here on making a big dent is going to be on what we call deep retrofits, right? Which are more of a holistic approach to addressing the performance of our buildings. And they can be a little bit more disruptive for sure in the buildings and maybe to the occupants. So, we're looking at potentially reconfiguring the interior, maybe adding windows, trying to rearrange the windows to kind of capitalize on daylighting. We are looking at potentially totally upgrading our systems to kind of have greener systems involved, whether or not that's ground source heat pumps or other types of technologies, which are a lot more invasive in terms of accessing the electrical grid as opposed to fossil fuels. And so when we look at retrofits, we're talking a lot here about energy use and trying to reduce carbon emissions, which is a big part of maybe why we're here today talking about this as a result of Local Law 97. But there's other reasons why and other considerations we need to have around retrofits, and thermal resiliency is one of them. understanding that we are having power outages too as a result of climate change, and how do these buildings perform when the power is out? How can they keep occupants safe and comfortable for a period of time before that power comes back on? We talk about durability. A lot of our buildings are starting to fall apart, right? A lot of our historic buildings don't have insulation, don't have airtight layers. They're starting to have mold. They're starting to have all sorts of issues. And so sometimes we're just addressing these buildings from a retrofit perspective to kind of improve their performance and improve their robustness. Sometimes it's just occupant comfort, trying to minimize the disasters that we've been seeing, particularly from the fire side across New York City. We had a catastrophe just a few weeks ago in the Bronx from space heaters that were being used because the buildings were not comfortable enough for the occupants to really live in there, without the supplemental heat of space heaters that can lead to major fires and other issues. So just trying to kind of address these types of issues are really important. And we shouldn't forget embodied carbon, right? As we start to improve the operational elements of our building to kind of reduce operational carbon, the embodied carbon component comes into play with the materials that we're choosing. Retrofitting for enclosure durability. So the term durability, we should just understand that, it is not an intrinsic property of a material or a system. It's really a function of that material or that system or that assembly and the environment that it's being placed in, right? So something that could be durable in the Pacific Southwest might not be as durable in the Southeast, right? In kind of a Florida hot, humid climate, or in the Northeast, right? So we want to understand, again, the environments that we're building in and understand how those assemblies fit. And so just a quick kind of overview on building science around the wall and understanding our enclosure functions. Whether or not we're talking retrofit or new construction, we want to understand these control functions and prioritize them effectively, right? And so rain and water control is always going to be number one in our approach. If our buildings are leaking water, odds are likely they're also leaking air. Our insulation is probably getting wet, so our thermal control is being reduced. And then the amount of vapor that we might have come into our buildings through just natural diffusion is fairly irrelevant if you already have standing water in your building. So we should always, as designers, focus on rain and water control. Rain screen kind of technology is a really good way and robust way to do that. There's other mechanisms as well. Air control, right? Having an airtight system is really important. If we have air leakage, that can be problematic in many fronts as well. With air leakage comes a lot of kind of energy loss, right? Heat energy being lost, either way, during the hot summer months or the cold, drier months. But air can also bring with it lots of moisture that could condense within our envelope and create all sorts of other issues. So air barrier systems are really paramount for performance. Thermal control as well, right? We need to make sure that these buildings are properly insulated so we're not losing heat. Vapor control is critical too, but we can't forget things like fire and smoke. Some of the major retrofits globally have had catastrophic fire failures, such as the Grenfell Tower in the UK, which was a retrofit for the use of foam plastics and some of the improper designs with those assemblies. So we have to think about fire safety in these solutions. And acoustics is becoming much more critical as well in terms of relating proper acoustics to the health and well-being of occupants and kind of how we're living in our buildings and how we're working in our buildings. So the goal here is to really find a nice balance between that energy savings that we're focusing on, but without compromising the durability and resilience of the enclosures, and certainly without compromising the health and the comfort of the occupants. So when we talk about existing buildings, particularly buildings that were built, let's say 20, 30 or more years ago, a lot of these buildings don't have much insulation. A lot of them don't have airtightness or water resistive barriers. And so when we talk about now retrofitting them and adding airtight and lots more thermal insulation, we're reducing the heat flow across these walls. And so basically what that means is these older buildings didn't have insulation, didn't have airtightness, they would get wet. You'd put the heat on in the inside and that heat would transfer through the wall and dry those assemblies out, or hopefully that was the case. But when we add this airtightness and this insulation, they're no longer able to kind of dry out from that heat flow transfer, or it's a lot more difficult. And so understanding building science, understanding that we should be thinking about vapor permeance within our assemblies to allow for diffusion to dry those assemblies out is really, really important. And so, it's critical when we talk about our layers for membranes, water resistant barriers that are vapor permeable, and insulation that is vapor permeable to allow for maximized drying. The use of rain screens can really help with this as well, providing a nice ventilation and drainage space for that outward vapor drive to dry things out. And I mentioned earlier, we're going to look at a couple of examples of exterior retrofits and an example of an interior retrofit. And so exterior retrofits are generally more favorable. So the reason for that is if you have an existing structure, again, that doesn't have any insulation or air tightness, if we start to add air tightness on the outside and then add insulation to the outside, we now know that our condensation or our dew point is going to happen safely outside of that historic structure, right? So it's not compromising the integrity of the building, the original constructed building. And so that's a pretty robust way to address retrofit. And again, sometimes we don't have that option, right? So sometimes we're dealing with lot line issues or historic preservation. And so we have to put that insulation on the inside, and we can do that. We just need to be a little bit more careful about the moisture and the condensation that we might see. So again, from an interior retrofits perspective, it's optimal with those lot line challenged buildings or historic preservation. Durability is definitely going to be a concern. So we have to understand the temperature profile in the assembly. Air tightness is key. And then operationally speaking, it's going to be a higher occupancy disturbance in terms of a retrofit. Obviously, it's more invasive. You're getting into the building. So whether or not we're talking about commercial buildings or residential buildings, the occupants are probably going to have to get out of the way when that work is being done. On the exterior, however, it's less impactful, lower occupant disturbance, right? Outside of maybe a bunch of scaffolding and contractors running around the outside of the building, you're not going to have to evacuate or get out. The condensation challenges go down, as I mentioned. We do have to understand what the weight of the insulation and the cladding are doing to that existing structure. And does that structure have the structural integrity to support all of that, or do we need to kind of supplement with more support? And of course, we want to think about fire performance with the materials that we're using, particularly on the outside of these buildings. All right, so Stonewool retrofit solution. So we're going to start first with maybe one of the more common approaches, which is just going to be your traditional overclad rain screen retrofit solution. And so we can see here on the right, this is the nice section detail of what this looks like, and it's really not too different from a new built retrofit. When we look at our assembly layers and those control functions, what you would typically see here is a peel and stick or a fluid applied air and water resistive barrier on the existing structure. You would then add some level of semi-rigid or rigid stone wool to the outside of that. And then you have your cladding, right? And rain screen claddings can be a variety of materials, from metal panels to ACM to high pressure laminates to fiber cements to porcelains to stones. And so a lot of those can be used in these types of applications. And when you come to the critical considerations here, again, you want to understand what is the structural capacity of that existing substrate. Can you attach to the existing brick? Do you have to peel back that brick to the more structural kind of components behind that existing building? What are the effective R value requirements of this retrofit if we're trying to meet local law 97? We want to understand that thermal bridging can be dramatically impactful. So how do we attach that cladding without creating too much bridging? We have to understand the integration of the details for the windows and the doors and maintaining air tightness and thermal control. And then, as I mentioned numerous already, the fire resistance requirements. And so the example building that we're going to look at is a job in New York City. This is at 201 East 79th Street. It was a building that was constructed back in the 1960s. It was one of these kind of wedding cake looking buildings that, are fairly ubiquitous, as you're strolling around Manhattan. But the masonry had, deteriorated. The tenants in this co-op building were tired of having to deal with local law 11 repointing. They had scaffolding up on this building all the time. And so they worked with Rogers Partners and Rawling Architects to really come up with a strategy to improve the aesthetic on the outside of the building, to take away these issues with local law 11, and to address the requirements, the looming requirements around local law 97 to meet that Plan NYC 2030 carbon reduction goal of 30%. So what they discovered was that their brick was in really awful shape. There was no thermal insulation. There was no water resistive barrier behind this brick. They really had no option but to take that brick off and to have it reclad. And they realized that obviously with local law 97, they needed to add that airtight layer and they needed to add a proper amount of thermal insulation to meet the 2050 requirements of Local Law 97. And so here are just a few images of what this is looking like. You can see on the left here, the fluid applied black membrane that was a vapor permeable membrane that was put over the existing CMU. They then added 5 inches of a semi-rigid Stonewool insulation to meet the thermal resiliency requirements of Local Law 97, as well as to meet the fire code requirements of non-combustibility. They had a thermally broken clip system to support a porcelain rain screen, which you can see here on the right. So that's kind of what that finished product looked like. And so when those, we talk about these clip systems, and this is something I talked about before the pandemic when I was here presenting last, is, again, we want to minimize thermal bridging. When you look at continuous girth systems to support rain screen claddings, if it's continuous and penetrating your insulation, it's really not not very efficient, right? At best, we're talking 50% effective when it comes to that R value. Moving towards these clip systems, which we are seeing on that project in Manhattan, can be much more effective. And there's now clip systems specifically geared towards retrofit that can run slab to slab, which can get up to much higher levels of efficiency, above 90%. You can move to fiberglass systems, right? So fiberglass, as opposed to metal, is much less conductive to really help boost that thermal efficiency of those solutions. This is not a retrofit, but this is a passive house building in Hoboken, New Jersey, that had an 8-inch clip to house 8 inches of semi-rigid Stonewool. And then you also have rigid insulations. And so here's a rigid Stonewool insulation that you don't require any clips or rails to penetrate. In fact, it has the compressive strength to support the cladding just with the use of fasteners connecting back to the structure itself. And now we're up in that 95% effective range. So you have a variety of options, but it's just important to think with these retrofit solutions, what is that kind of clip system looking like, and how do we maximize the efficiency moving forward? All right, so now we're going to move on to a second case study, which is an Efus retrofit, so an exterior installation finish system. And probably many of you out there are very familiar with foam-based Efus. And so that's a very commonly used approach here in the United States. But what I'm here to talk to you about is a retrofit solution that actually used a Stonewool-based Efus system. So there are Stonewool solutions out there, and you can see the section detail here on the right. And similar to maybe the Efus systems that you're used to, whether or not it's new construction or retrofit, your primary air barrier is going to be typically a fluid applied product that comes as part of a system that goes over your existing substrate. And in this case, we're talking about a semi-rigid or rigid Stonewool insulation that requires a level of mechanical fixing. So it's a little bit different from your foam insulations, that these ones will have levels of mechanical fixing as well to keep the product in place. And then you have your finish and your reinforced mesh on the outside. So, with any Efus system, right, the critical consideration is going to be integral drainage, right? And so that can be done with adhesive ribbons in this type of solution. The Stonewool itself is drainable, which is beneficial, but you can also create geometric dimensional drainage cavities behind the insulation, which is commonly done. We want to think about kind of the superior board quality, that it shouldn't be a low density Stonewool. These are typically high density products, and oftentimes they come at dual density, where you can actually have a softer density against the substrate to conform to any of the irregularities of the substrate, and then on a more rigid outer surface to allow for that rendered mesh to fit effectively. The other thing is fire resistance, and oftentimes we see the movement towards Stonewool to meet either fire code requirements or the sustainability requirements of trying to reduce VOCs, to try to reduce embodied carbon within these systems. And so the case study we're going to talk about here is not in New York. It's in Hamilton, Ontario, not too far from Toronto. And this is a project called the Ken Sobel Tower. It is a low-income housing building that had been around for many, many years. I forget how many decades it had been in existence. But the developer and the owner of this building was really concerned that the envelope was deteriorating. They had to vacate the building. There was no insulation. They had located mold and other types of hazardous materials, no thermal control, and most of the mechanical systems were at the end of life. And so the owner really wanted to tear this building down. And so it wasn't until they connected with ERA Architects, which was a local architect, who really spoke to the fact that, from a carbon perspective, the worst thing we can do is tear this thing down and rebuild, that we need to salvage this. The most green building that's out there is the one that we don't have to build again. So again, this was kind of the emphasis and the focus with this retrofit. And so it was going to remain an affordable housing building. And the goals here from ERA and the owners were to really create an ultra low energy retrofit that maintained the affordability of the building, particularly from the occupant's perspective. And so they wanted to reduce greenhouse gas emissions from a sustainability perspective by 90%. And so the way that they had to do that was through Passive House, right? And so Passive House, for those of you who are not familiar with it, is really a mechanism to improve the building's performance and again, reduce the emissions, reduce the energy use for heating up to 90%. And there are retrofit strategies under the Passive House Institute in Darmstadt, Germany, as well as the Efus Institute here in the US. So they wanted to reduce the thermal bridging. They wanted to kind of understand climate resilience and the safety of the occupants, many of whom might not have places to go if they needed to evacuate in a blackout. So understanding kind of how they could shelter in place was a big part of this. It was paramount to have fire resiliency. They did not want to use any sort of combustible products on the outside of this building. And so that's kind of what led them to the use of the Stonewool solutions. And so we can see here what this looks like, right? You can see some of the mechanical fixing on the 6-inch rigid Stonewool that's used here in the center. You can then see the reinforcing mesh and the base coat here on the right. So just to kind of introduce you and give you kind of a sense of how this type of a solution would work. And I've used kind of climate resiliency, and I've used the term passive survivability a few times in today's program. And so just to kind of connect the dots there, this is something that ERA really wanted to focus on. And so what we're looking at here is kind of a comparison between the original design, or what was there as an existing design, and the retrofit solution. And so we can see here, this is in Hamilton, Ontario. It's very cold there during the winter, but we are in Celsius mode because that's kind of where they are. And you can see this black line at the bottom is just representing what the outdoor temperature is during this time of year. And so you can see it's all below 0 degrees Celsius, all below the freezing mark here in the US. And our blue line represents the interior temperature of that building as it was originally designed, right? The red line represents after the retrofit, what the interior temperature would be. And the vertical black line is kind of signifying our power outage. So we're having a power outage in the middle of winter. And with this blue line, that original design, you can see within a matter of minutes or even hours, we've dropped the interior temperature below the survivability line, which is the threshold for that is 15 degrees Celsius. So what that means is the occupants in that building, if there was a power outage, just within a few minutes or a few hours, it really would be inhabitable, particularly for occupants that have any sort of health challenges or elderly. If you have very limited time to evacuate, that could be very problematic. The retrofit design you can see here keeps that interior temperature hovering above the survivability line for almost 2 days. And so that's the hope, is that within 2 days, we can get the power up and running, or we can find more effective ways to evacuate people from this building. And so that's, beyond the argument around energy performance. Now we're talking about the safety and well-being of the occupants, which is a really big deal. They also did this study during the summer heat wave, and they identified that the original design, getting some feedback, the original design would have created problems within a half a day compared to 4 days of being able to shelter in place with the proposed retrofit design. So really big deal in terms of life safety. All right, so now we're going to switch gears and move to the retrofit solution for the interiors, that is. And so what we're looking at here on the right is, as opposed to having our solution put on the right side of this, right, on the exterior of the building, we're looking at maybe a masonry wall, a historic building, where we don't have the opportunity to put insulation on the outside, so we're putting it on the inside. And so with these solutions, your primary air barrier, unlike on the other solutions, which were on the outside, is going to be on the inside of that structure, right? If it's like we're talking, let's say 3 or 4 wipes of brick, it's going to be on the inside of that brick, typically done with a fluid applied vapor permeable membrane. The thermal control, you still want to get as continuous as you can. So using a semi-rigid product adjacent to the structure is going to be really important. And then we want to introduce a secondary air barrier that provides a level of vapor control. And so this is going to be what we call a smart vapor control layer. And we call it smart because in these environments, particularly in our climates, we want any of that warm interior air that's going to be trying to make its way into our assembly to stop, right? But what we don't want is we don't want the ability for this building to dry to the inside when it needs to dry to the inside, right? Because this brick might not be used to getting wet and staying wet. And so over time, we want to give it an option to dry to the inside. And that's what these smart membranes do. So if the RH level starts to get very high, the pores of this membrane open up and allow for interior drying. And so that tends to be a really important part, particularly when you're dealing with vapor permeable, air permeable insulation like Stonewool. Critical considerations here, we want to understand the quality of the brick, right? So if we have really crummy brick, odds are likely if you start to add insulation to the inside and that brick gets wet and stays wet and freezes, it might not be in good condition anymore. And so you always want to do core sampling of these materials to ensure that it's a quality enough brick that it's going to be able to survive this type of a retrofit. And so we see that quite often in these assemblies, and that's certainly a recommended approach. And again, we want to make sure that we're enabling that interior drying, right? So these smart membranes really are important from a durability and a robustness standpoint. And so here's the project example. It's in Brooklyn. It is a project in Flatbush at 1701 Albemarle Road. And so before I jump too deep into it, it was not the entire building, or it's not the entire building yet that's going through the retrofit. In fact, it was a single tenant who wanted to kind of emulate and show when they're turning their apartment over, that the opportunity for each owner of a single unit or a co-op to contribute to Local Law 97 and addressing those needs, particularly in these historic buildings, right? So they wanted to comply with Local Law 97. This tenant in particular wanted to try to comply to the Passive House retrofit standard. I don't know if that's where they ended up, but they wanted to kind of look towards doing that. They also wanted to maintain the historical integrity of this building, and they didn't want to use any solutions with foam that could be non-modified moving forward. They wanted to be able to kind of pull these things out at some point in the future as need be. And then there's obviously the VOC challenges as well as the combustibility requirements. And so you can see here on the left, this is the pre-retrofit buildup after they took the sheathing off. So I think it was like 4 or 5 weights of brick, really in good condition. They did do some core samples of this. The post retrofit buildup, at least semi buildup, was these 3 inches of semi-rigid stone wool on the inside. And as we look at this next few images, you can see the fluid applied membrane that was applied to the inside of the brick here. And then you can see here on the right, the smart vapor control membrane that was then draped over that continuous insulation. And there was a narrow stud wall that was, kind of placed to the inside of that, where they actually added additional lower density batt stone wool insulation as well. And so what this also does, this kind of sequence, it kind of helps protect and kind of keep this membrane protected from the hammers and the nails and the electrical conduit that might be being applied from the contractor beyond that, or if somebody's putting a painting on a wall, you're not going to be penetrating this air and vapor control layer. It's sandwiched nicely in between the 2 thicknesses of insulation, and it gives you that stud cavity to really have any of those service chases going. So again, just from a kind of recognizing the performance moving forward, that was a nice way to address that challenge. So now we're going to move on to some additional considerations, right? And I mentioned this earlier, operational carbon is a big deal. And so we're retrofitting buildings and we're starting to move towards high performance, low energy buildings to reduce that operational carbon. But as we do that, we also have to realize that the chunk of the pie that makes up the embodied carbon starts to get bigger as we reduce the operational carbon. So thinking about embodied carbon of our materials is very front and center these days. And that applies to all the materials in the building, not just insulation, but we're talking obviously about insulation here today. So I'm just kind of providing this chart from Architecture 2030 and 2030 Inc., kind of comparing and contrasting the embodied carbons of different materials that are used as commercial and residential insulation. And you can see here, the biggest offenders are really some of those rigid foams, the XPS, as well as the spray foams. Those tend to be some of the worst performers. Some of the better performers, tend to be more of these organic materials that might not have the fire performance requirements that we would hope for, or the commercial availability and the testing around that. And I think there's still some movement there. But some of the really strong benefits of mineral wool or stone wool or fiberglass, kind of middle of the pack as far as embodied carbon, but really providing a lot of the other values that you would need acoustically, fire-wise, from insulation. So we do see a lot of movement towards stone wool and mineral wool as a result of this kind of embodied carbon shift. And so when it comes to embodied carbon and stone wool in particular, or mineral wool in particular, we also want to recognize that all manufacturers have a little different statement here. And so there's some industry averages that you can find for both the lower density blanket or bat insulation, as well as the boards. And then even within the manufacturers within the industry, there's some differences. And what's unique here is that the slag wools, or the products that actually have a higher recycled content, which might be perceptibly a greener product because of recycled content, actually have a much higher embodied carbon than those that might have more of the virgin natural stone, which also provides a more robust performance product. So, you want to look at things a little bit more holistically. And with that being said, embodied carbon is really important. It's a very hot topic right now, as it should be. But there's lots of other considerations that we should have around sustainability and product choices. And so looking for manufacturers that have environmental product declarations that provide the information about what the materials are in those products, that speak to circularity, that talk about cradle to cradle initiatives, within those products, all really important information. We also want to realize that ozone depletion is a separate entity from carbon emissions, and certain products that might have good carbon emission statements might be worse at ozone depletion than those that are not. So you need to look at that as well, as that's a paramount discussion. I mentioned circularity. Are these products that you're using able to be reused again? As we're starting to build, as we should, kind of construction to deconstruct, right? And understanding that the buildings that we're building today might be used somewhat differently in the future, looking at materials that can be taken out of construction and put back in a different manner. Also really critical. Proper application is super critical. I already talked about thermal bridging, right? We don't want to, if we're using a low embodied carbon material and spending more money on it and trying to get a better operational carbon out of it, if we throw it in between a bunch of studs or lots of thermal bridging, then it's not doing what we want it to do. So we want to think about the application and trying to maximize efficiency of materials. And then last, but certainly not least, health and safety of occupants with those materials, and thinking about fire safety is a strong consideration. I referenced this earlier, which, this is the Grenfell Tower images from over 5 years ago. It's getting crazy in terms of time, but, this was a retrofit building. And while the foam plastic wasn't the sole source of this fire, the 76 fatalities that occurred were due to the smoke inhalation from the toxic foam that was or the toxic smoke that was from the foam plastics, both on the outside of this building as well as the inside. And as a result, the retrofit initiatives in the UK, as well as new builds, have put a ban on the use of combustible materials, whether or not that's insulation or claddings on the outside of those buildings. And New York City actually just implemented some really strict requirements around the use of combustibles in New York City. And when we talk about moving out of the city, or talking out of the jurisdictions that we might live, we're seeing a lot more forest fires, wildfires occurring all across the United States, all across the world. Here in New York, we actually had smoke coming from California late last year from some of the wildfires that were occurring there. And when we look at this kind of cross section of trying to improve energy efficiency and dealing with wildfires, there are a lot of concerns out there, particularly, let's say, in California, where their energy codes on the residential end are starting to demand more exterior insulation. But tenants are concerned because they don't want to add combustible insulation, rightfully so, to the outside of their buildings. And so the UL Fire Service in California did kind of this testing to kind of analyze the wildlife urban interface. And they were analyzing two solutions, one that used XPS insulation on the outside of the building, and one that used a rigid stone wall on the outside of the building. And to emulate kind of the wildfire or just a natural fire from, let's say, a barbecue that's been placed next to the building, they wanted to kind of see how this fire manifests up the vinyl siding and into the building. And so we're just kind of looking at these two test assemblies. The clock for the Stonewool, we've sped up here because what we noticed was, even after 30 minutes, you'll see, the fires burnt away the vinyl siding, but then it just dies on the vine, right? There's nowhere for it to go beyond this non-combustible Stonewool insulation. However, the XPS solution above, you can see that the flame is now spreading dramatically and creating a tremendous amount of toxic smoke as it travels up this building. And we see that right at the 3-minute mark, there's going to be a flashover into the attic. There it goes. And you can see then they have to diffuse that quickly. Just really kind of showcasing the difference here in the types of materials that we're using to address these kind of climate initiatives. Other things to consider with insulation, right? R values are not constant. We should understand that over time, some R values will decrease with materials, as well as when we look at temperature dependency and the fact that at different temperatures, R values will shift. And so what we're looking at here is kind of the comparison between stable and unstable R values. And so Stonewool, really any fibrous insulation, derives its R value from the trapped air between those fibers. And that air is not going anywhere. If it does, it's replaced by more air. And so we like to call this very stable. Semi-rigid Stonewool, which is used for continuous insulation on buildings, is going to be an R4.3 per inch. Today, it will be an R4.3 per inch a century from now. Right? And there's a lot of studies around that. When you look at foam insulation, whether or not that's polyisocyanurate or XPS, they use blowing agents within the cellular structure of their products, which will off-gas over time, which isn't great for a variety of reasons, but from a thermal perspective, it equates to a 20% R value loss for the polyisocyanurate sometime between year 2 and 20, and it's about a 10% loss in the extruded polystyrene. So again, when we talk about designing for durability and resiliency, we want to understand and ensure that we're getting the performance over time that we expect. Temperature dependency. What we see here is, nominal R values of any sort of insulation are going to be taken at 75 degrees Fahrenheit. We're looking at a host of insulations here, from spray foams to cellulose to mineral wool to fiberglass to the rigid foams, and kind of they're compared here with these dots at 75 degrees Fahrenheit. But I would venture to guess that many of us are not too concerned about the R value of our product when it's 75 degrees out. We're probably more concerned when it gets a lot colder. And so you can look here, right? A mineral wool semi-rigid product is going to be R4.3 at 75 degrees, but it actually jumps up to 5.1 when it's 0 degrees out. And the one outlier here is the polyisocyanurate, which starts to decrease its R value at about 55 degrees Fahrenheit. And so what does that mean? So whether or not we're talking about, comparing roofs or comparing walls, we might, look at a nominal R value comparison to polyiso, which might be listed at 5.7 or even above that, to a semi-rigid Stonewool, which is at 4.3. But really, once we hit 25 degrees, it's a crossover point where the Stonewool actually starts to outperform that polyisocyanurate. So we want to understand kind of the temperature role here in thermal insulation. The codes, particularly in Canada, have started to outline requirements for manufacturers to list their R values at varying temperatures. I don't think that's yet in the cards for the US, but it's something that as a specifier, we should understand, particularly for the well-being of the clients that we have and the expectations on performance. All right. So just in summary, before we get to the questions that Ron has in his possession, I'm just going to kind of put things together here, right? So climate change is real, right? Our existing buildings are big contributors to greenhouse gas emissions. So in order for us to make a dent, these deep energy retrofits, really need to start taking place and have to take place at a much higher pace. And so in New York City, at least, we have these the mechanisms to do that through Local Law 97 and some of the policies that are coming down the pipe. But we can't forget other benefits from this, right? Passive survivability is a natural byproduct of these effective energy retrofits, right? So it's keeping our occupants safe. When we look at doing, low-income housing, senior housing, any sort of building that's occupying vulnerable populations or folks that might not have the same means to evacuate that many of us do, passive survivability shouldn't be an oversight. And then, reducing operational carbon emissions is critical, but we still, again, can't overlook other critical considerations. We talked about durability, right? We want these changes to last. We don't want to have to spend more operational carbon sometime down the line to have to re-retrofit these buildings. We want to look at embodied carbon and the materials that we're choosing, because that's a critical component here as well. Can't forget things like ozone depletion. Certainly can't forget about things like life and safety around fire performance. And we want these buildings to last the test of time. So all those things are really important to kind of consider as we're approaching any retrofit, from single family houses to large commercial buildings. But thank you for your time, and I'm going to throw it now back to Ron for questions.
Great. Thank you for the excellent presentation. And let's see, here's some questions. So first, is Tyvek considered a smart vapor barrier?
Tyvek is not considered a smart vapor barrier. So Tyvek is it's a high permeable vapor, permeable air barrier. But really the smart vapor control layers, many of them are based out of the material nylon, which just has this natural component of as the RH levels change, the pores of the material change to make the material vapor variable. So again, if you had a high RH level on the inside of a building, pushing up against the Tyvek, it would remain vapor open to allow that moisture to move, which is what you're trying to avoid. Whereas these other products, in the moment of the high vapor movement, will stop it dead in its tracks. The smartness of it is that if you have, let's say, trapped moisture for a long period of time, the pores will eventually open up. And so there are probably 4 or 5 products that are out there on the market right now that are available that are smart, that are considered smart membranes that I'm aware of.
Great. Thanks so much, Todd. So painted gypsum board to some degree impedes drying to the inside. Doesn't that trap moisture in the wall assembly and possibly damage the interior finish?
So I think it depends on the paint that you've got, but typically I don't remember what the vapor permeance of the drywall is, but there is some level of drying to the inside in those cases, and so it's typically, I think, meets either class 2 or class 3 from a vapor retarder perspective, which is kind of what we would want in a lot of the areas in and around New York.
Cool. As someone who represents a non-foam insulation alternative to this spray foam crazy construction environment, how can I get my firm to get away from specking spray foam?
You can reach me on my email, which I'll provide, and we'll give you all sorts of opportunities to look at that. I mean, there are some benefits for sure to spray foam if you're not concerned about fire safety or VOCs or things of that nature. Spray foam is air, water, vapor, and thermal tightness all in one layer. But you really have to understand that it needs to be applied properly at the right thickness. And that, if it's not done right on the right surfaces, it can crack, from expansion and contraction, which can be very compromising long term. And so we can get into all those specifics, but there are options with mineral wool that can potentially alleviate those challenges.
Great. What is the comparative cost of Rockwool, XPS, and poly?
In the New York metro area, I mean, it's going to be a function of thickness and kind of what you're looking for, but pound to pound Stonewool in our market, particularly as you're looking at exterior insulation on walls, Stonewool or Rockwool is going to be less expensive than those other products. As you start to compare and look at roofing products, it's going to shift when you get into higher densities. So it's not an easy question to answer offhand, but we can certainly follow up afterwards, and we can get you that kind of comparison.
Great. During the construction phase, what happens if the Rockwool gets wet?
So that's a great question. So when we look at lower density bat insulation, the benefit with any Rockwool products is that they're hydrophobic and they're drainable. If you have these product under a hydrostatic head, it will eventually seep into the product, but it will drain and dry out. So if you had, compared to fiberglass bat insulation, the benefit of a Stonewool insulation is if it gets wet on a job site, you just let it dry out for a period of 24 hours where it can actually drain at the bottom and the product is not compromised. When it comes to our semi-rigid or rigid products for the outside of the building, Those can be exposed, and it's similar to what I just said, but they even have additional binder content and oils to make them more hydrophobic. But they can be used in open joint rain screen. They can be used for below grade foundation wall, which is commonly done under slab. So they are meant to be interfaced with water, and they're not compromised, in those applications.
Excellent. So do you see local law 97 becoming the type of legislation that's going to be statewide and broader?
That's a great question. I think Kathy Hochul will have to answer that. I think she's very focused with a lot of these kind of climate initiatives as well. I wouldn't be surprised if we started to see the adoption of some of those policies moving, kind of upstate. So I think we everyone's watching New York to see kind of how this manifests. I know in Massachusetts, Boston has just kind of instituted very similar policies to New York. So people are starting to adopt what we're seeing here. And I think a lot of people are starting to move towards these types of solutions. I can speak firsthand that not a week goes by where I don't have somebody knocking on my door or sending me an email or a phone call, trying to understand how to retrofit their large scale buildings. So it's happening pretty rapidly here.
Well, Todd Kimmel, thank you very much for this excellent presentation. What were you going to say? Go ahead.
I wanted to connect the dots, if you don't mind. I had some Rockwell content that I just wanted to share if we have a couple minutes.
Sure. Yeah, go.
So I wanted to make sure I did it after the questions and answers. I guess I'm disabled in terms of sharing. I don't know whether or not there's a way to allow me to reshare my screen.
No, you should be able to. So go ahead, try again, please. I'm sorry.
It's telling me.
Wait. Here we go. There we go. There you go.
All right. Thank you. Hold on. And so just kind of connect the dots. I didn't say much before the presentation. And it sounds like many people are familiar with Rockwell, but our primary business operation is commercial insulation here in the U.S. But we do have a sister company, Rockfon, that uses the same Stonewool technology for acoustic ceiling tiles. So if you guys ever have a need for that, the robustness and the acoustics are there as well. And we have a few other divisions that are not as prevalent yet in the U.S., but certainly very popular globally. As I've reiterated through the program, right, the benefits of using Stonewool Rockwell insulation is the non-combustibility aspect, the thermal stability, the water repellency that we just reiterated, the fact that it's vapor permeable, which is really important for these retrofits and high performance buildings, and the sound absorbency and kind of getting to those more acoustical, high performing assemblies. We don't just provide, as you know, just a bat insulation. We have a variety of products for a variety of applications on the interior and the exterior of the building. Even when it comes to curtain walls or fire safing, we tend to be very prevalent in those applications. And when it comes to embodied carbon, we do use energy to make our product. We were kind of middle of the pack there, as we described. But when you look holistically over the lifetime of the building, the Rockwell, let's say, that was manufactured and sold in 2019 is going to save 100 times the carbon emitted during its production, because it can last a long time and perform a long time. And so I'm proud to be an employee of Rockwell. We have aligned ourselves as a company with 11 of the 17 sustainable development goals, that were put forth by the UN. I'm not going to get into kind of all the things that we're doing to align with these goals, but they're very tangible things that we're trying to do and really measure. We understand that we need to improve our carbon emissions as well. We have goals to do that. We have now 2 facilities that are using electric cupolas to manufacture these products. We've moved to gas away from fossil fuels in a lot of the facilities, including our new facility in Ranson, West Virginia. And then even with our buildings, our office spaces, we're moving and retrofitting those buildings ourselves. This is one in the Netherlands that we did to the Passive House standard and trying to reduce the energy use. As I mentioned, products, we have low density bat insulation, much more robust than fiberglass for these types of applications. If you're trying to meet living building challenge, we have some great products that can do that in terms of no formaldehyde within the interior applications to meet those declare labeled red list free applications. On the exterior of the buildings, the semi-rigid product that we use commonly in rain screens is Cavity Rock. This is an image from the LaGuardia Terminal B that we did a couple of years ago. We have now a black face product that we saw on the project reference earlier in my presentation for open joint claddings or perforated claddings. And these are some more images from that retrofit. And then we have these rigid boards where, again, you don't need clips or rails. This is called Comfort Board 110, and this is an image from a passive house in Queens. This is the Corona Senior Housing Facility. And again, the only penetrations in this installation are the fasteners. And didn't talk about it a lot, but we actually did a retrofit of the Empire State Building with our roofing product. So we do have materials there to kind of provide those needs as far as hybrid solutions or full-on Stonewool solutions with all sorts of different membranes, and we have warranties to kind of back up with those solutions. So last but not least, a really great service that we offer to the market is this complementary building science. We talked a lot about hygrothermal analysis and moisture challenges. Rockwool provides these types of services to analyze our assemblies and your designs to make sure that there are going to be, that there's a lot of integrity behind that. We can do thermal bridge analysis, point thermal bridges. We can also do effective R-value calculations, and we've just expanded to add acoustic services as well. So if you guys are needing to analyze STC ratings or OITC ratings of your assemblies, we can support you there. But I just thank you for that time, and I'll throw it back to you, Ron, if there's any other questions, and let you guys wrap up. But thank you, everybody, for allowing me to come in.
So we'll send your information to everyone so that they have it and they can get in touch with you. Thank you very much, Todd. Once again, fantastic. So look forward to having you live sometime and maybe this year. So thanks everybody for tuning in.
Thank you, folks, and thank you to our sponsors, Rockwool and Ice Air, Bot & Company, Bright Energy, Home, Westchester Home, the one and only Michael Murphy of Murphy Brothers Contracting, and Ron Kamen with Earthkind Energy Consulting. Go clean, save green, everybody. Thank you very much for joining us. We look forward to seeing you next month. Have a great one all. Take care.
Thank you all.
Thanks,
Bye,
everybody.
Todd.